A blister, that's all it took. In the summer of 1924, the 16-year-old son of the President of the United States played tennis on the White House lawn without socks. A small blister opened on the third toe of his right foot. He barely noticed it. Within days, he was running a fever. Red lines were creeping up his leg, and the swelling in his groin told the doctors everything they needed to know. 7 of the finest physicians in America were called in. He was moved to Walter Reed, one of the best hospitals in the country. His father was the most powerful man on earth. None of it mattered. 1 week after that tennis game, Calvin Coolidge Jr. died in his father's arms. Understand what that meant. Not a disease, not a plague, a blister. In that world, every scratch, every thorn, every kitchen knife that slipped, every child-scraped knee carried a quiet possibility of death. Mothers died days after giving birth, from infections carried in on the hands that delivered their babies. Pneumonia walked into a house and took the strongest man in it. Doctors could clean a wound, cut it open, drain it, amputate the limb, and then stand at the bedside and wait, because waiting was the treatment. 4 years after that boy died, in a cluttered London laboratory, a Scottish bacteriologist looked at a dish he should have thrown away and saw something that could have ended all of it. And then, almost nothing happened. For more than 10 years. This is the story of how the most important medicine in human history was found, ignored, nearly lost, and finally dragged into existence by a handful of people working in the middle of a war. And of the man who paid for that delay with his life. Stay with me to the end, because the part everyone gets wrong is the part that matters most. The world of the small wound. To understand what penicillin changed, you have to stop thinking about medicine and start thinking about ordinary life. Imagine a farmhouse kitchen in the 1920s. A woman is cutting bread, and the knife slips across her thumb. She wraps it in a cloth. 2 days later, the cut is hot and red. On the 4th day, a thin red line is climbing the inside of her arm toward her elbow. Her family knows what that line means. Everyone in that era knew what that line meant. There is no medicine to give her. There is no injection. There is a doctor who will come, look at the arm, and speak carefully about how strong she is. This wasn't rare. It was the background noise of human existence. Blood poisoning from ordinary wounds filled hospital wards. Surgeons who cut themselves during operations died of the infections they were operating on. A splinter under a fingernail, a horse's bite, a nail through a boot sole, a burn that blistered and broke. Every one of these was a coin toss. Childbirth was worse. Puerperal fever, an infection of the womb after delivery, usually caused by streptococcus, arrived on the 3rd or 4th day when the danger seemed to have passed. The mother would spike a fever, her belly would harden, and she would die over the following week while her newborn was carried out of the room. Entire families were reorganized around this. A man might bury 2 wives before he turned 40. And then there was pneumonia. It was called the old man's friend, which sounds gentle until you learn what it actually meant. A way of dying so common that people had made peace with it. But it did not only take the old. It took children. It took soldiers. It took strong men who had walked to work on Monday and were dead by Saturday. Look at a family photograph from that time. The stiff collars, the unsmiling children arranged by height. Now understand that the parents in that picture assumed, quietly and realistically, that they might not raise all of those children to adulthood. Not because of war, not because of famine, because of bacteria. That was the world, and what medicine could offer against it was almost nothing. What a doctor could actually do. It's tempting to imagine that doctors in the 1920s were simply ignorant. They weren't. They knew exactly what was killing their patients. Germ theory was decades old. Physicians could take pus from an abscess, culture it, put it under a microscope, and name the organism. They could tell a family with real confidence that the patient had a staphylococcal septicemia. They could describe how it entered, how it spread, and what it would do to the heart and the kidneys. They just couldn't stop it. Everything in the medical arsenal worked before the infection reached the blood, not after. Antiseptics, carbolic acid, iodine, mercury compounds, could kill bacteria on a surface. Poured into a living wound, they killed the patient's own tissue at least as efficiently as they killed the microbes. And the microbes hiding deep in torn flesh survived anyway. Surgeons could cut infected tissue away, drain abscesses, amputate limbs ahead of the spreading line. That was real medicine, and it saved real lives. But it was carpentry, not chemistry. You cannot amputate a bloodstream. One young Scottish doctor learned this lesson in the worst possible classroom. During the First World War, Alexander Fleming served in a military hospital in Boulogne, France, working in a laboratory improvised inside a casino. He watched wounded men arrive from the trenches with shrapnel injuries packed full of soil and shredded uniform. The standard treatment was to flood the wounds with strong antiseptics. Fleming studied what actually happened, and what he found was damning. The antiseptics ran along the surface of the wound, while the bacteria multiplied in the deep, ragged pockets where the chemicals couldn't reach. And meanwhile, the patient's own white blood cells, his natural defense, were being destroyed by the treatment. Men were dying of gas gangrene and sepsis, while doctors did something that was, at best, useless. Fleming published his findings. Almost nobody changed their practice. He came home from that war with a question that would shape the rest of his life. Not, how do we kill bacteria? Bleach kills bacteria. The question was far harder. How do you kill bacteria inside a living human being without killing the human being? For almost everyone in medicine, that question sounded like a fantasy. And then, one September morning, the answer appeared on a dish that should have been thrown in the sink. The plate that should have been washed. Fleming's laboratory at St. Mary's Hospital in Paddington, London, was a small, cramped room in a corner turret, barely bigger than a closet, stacked with culture dishes, jars, and the accumulated clutter of a man who was famously untidy. He kept old plates around for weeks, coming back to them out of curiosity long after most bacteriologists would have sterilized them. In August 1928, he was studying variations in Staphylococcus aureus, the bacterium behind boils, abscesses, and the sepsis that had killed the president's son 4 years earlier. Before leaving for a family holiday in Suffolk, he inoculated a series of plates and stacked them on a bench out of the sunlight to make room for a colleague. He returned on September 3rd. Sorting through the pile, he found one plate that was different. A patch of blue-green mold had taken hold at one edge. That, in itself, was nothing. Laboratory contamination was routine, an annoyance, a wasted plate. But around that patch of mold, in a clear halo, the Staphylococcus colonies weren't just failing to grow. They were dissolving, fading into transparency, dying. The popular version of the story says the spore blew in through an open window. That version is almost certainly wrong. Fleming's window was rarely opened. His windowsill was crowded with tubes of dangerous bacteria, and opening it over a busy London street would have been reckless. What historians have pieced together is stranger and more human. In the room directly below Fleming's, a mycologist named Charles Latouche was working with molds, cultivating samples for research into asthma. Spores from that room appear to have drifted up the stairwell and into Fleming's lab. Then came the weather. London had a heat wave in mid-August, followed by 9 unusually cold days starting on the 28th. Penicillium mold thrives in the cold. Staphylococcus does not. If the plate had sat at a steady summer temperature, the bacteria would have grown up fast and thick, and the mold would have arrived too late to show anything at all. The clear halo only appeared because the mold got a head start, because London had a cold snap at exactly the right moment in exactly the room below a man who never cleaned up. Fleming didn't shout. He didn't run down the hall. According to those who knew him, he looked at it for a while and said something close to, "That's funny." Then he did the one thing that mattered. Instead of washing the plate, He saved it, and he started asking what the mold was doing. Mold juice. What Fleming did over the following months was careful, patient work. He grew the mold in pure culture and found that the killing agent wasn't the mold itself. It was something the mold was releasing into the liquid beneath it. A substance. For a while, he simply called it mold juice. On the 7th of March, 1929, he gave it the name it still carries, penicillin, after the mold that made it. Then he tested it against everything he could get his hands on. The results were remarkable and frustrating at the same time. Penicillin destroyed Staphylococcus. It destroyed Streptococcus, the organism behind puerperal fever and scarlet fever. It destroyed the bacteria behind pneumonia, diphtheria, meningitis, gonorrhea. Against the typhoid bacillus, it did nothing. It didn't kill everything. But the things it killed were precisely the things that were killing people in ordinary life. And here was the part that should have stopped the world. It appeared to be harmless. He dripped it into a rabbit's eye. He put it on healthy tissue. He watched what it did to white blood cells, the very cells that antiseptics destroyed, and it left them alone. He had found something that killed bacteria without killing the patient. The impossible question from the trenches had an answer sitting in a dish on his bench. On the 13th of February, 1929, Fleming presented his work to the Medical Research Club in London. The chairman of that meeting, one of the most influential figures in British medicine, later admitted that he hadn't sensed anything striking in the talk at all. No questions, no excitement. Fleming published the findings in the British Journal of Experimental Pathology later that year. The world turned the page. Part of the blame belongs to Fleming himself. He was shy, undramatic, a poor public speaker who reported his results without argument. But most of the problem was real, and it was chemical. Penicillin was fantastically unstable. The active substance was present in tiny amounts in a soup of mold broth, and it fell apart when you tried to concentrate it, undone by heat, by acid, by time. Fleming tried to purify it. He asked chemists to help. A team at the London School of Hygiene tried and failed. His assistant, Stuart Craddock, sick with a sinus infection, was treated with the crude broth in January 1929. It didn't work, almost certainly because the organism involved was one penicillin couldn't touch. By 1929, the work at St. Mary's had effectively stopped. Fleming had found the most powerful drug in medical history and could not get it out of the bottle. 10 years of silence. Here is the fact that should sit uncomfortably with anyone who believes good ideas succeed on their own merits. For more than a decade, penicillin existed, was published, and did almost nothing. Fleming didn't abandon it entirely. He kept the mold alive. He grew it, subcultured it, and sent samples to any laboratory that asked, free of charge, for years, hoping that someone, somewhere, had the chemical skill to finish what he couldn't. Nobody did. Meanwhile, the search for a cure went in a different direction, and for a while it looked like the right one. In Germany, a pathologist named Gerhard Domach found antibacterial activity in a compound derived from industrial dyes. It was called Prontosil, and it had an odd property. It did nothing to bacteria in a test tube, but it saved infected animals. French researchers explained the paradox in 1935. The body broke Prontosil down into an active fragment, sulfanilamide. The sulfa drugs had arrived. They were a genuine breakthrough. In 1936, the son of President Franklin Roosevelt lay in a hospital with a streptococcal infection of the throat that was expected to kill him. He was given the new German drug. His fever broke. He walked out of the hospital a month later, and American newspapers ran the story of the miracle on the front page. By 1937, sulfa drugs were standard treatment for pneumonia, meningitis, and scarlet fever. So the world had something. It was imperfect. Sulfa drugs had real toxicity, real failures, and a limited range. But it was something, And something is often the enemy of everything. Why chase an unstable mold extract that nobody could purify when a synthetic pill from a factory already worked half the time? The mold sat in laboratories across Europe and America, quietly growing, waiting for the right people to look at it. Those people were about to be brought together by the worst catastrophe of the 20th century. An Australian, a refugee, and a man who fixed things. In 1936, an Australian pathologist named Howard Florey became director of the Sir William Dunn School of Pathology at Oxford. Florey was not a warm man. He was blunt, driven, impatient, and utterly uninterested in charm. He was also brilliant at something rarer than genius, assembling people who could do what he couldn't. One of his hires was Ernst Chain, a German Jewish biochemist who had fled Berlin in 1933 with almost nothing. Chain's mother and sister stayed behind. They would die in the camps. He was volatile, gifted, and combative, and he and Florey argued constantly for the rest of their working lives. In 1938, Chain was doing something unglamorous, combing through old scientific literature, looking for antibacterial substances made by living organisms. He came across a 9-year-old paper by an obscure bacteriologist named Fleming. What caught his attention wasn't the medical promise, it was the chemistry. A substance this unstable, this hard to isolate, that was an interesting problem. They applied for money. British funding bodies offered a fraction of what was needed. The Rockefeller Foundation in America came through in 1939 with a grant. And then, in September of that year, Britain went to war. Everything about the penicillin project ran against the grain of wartime Oxford. Materials were rationed. Equipment was impossible to get. Young men were being called up. And yet the war also gave the work a terrible logic. In every conflict in history, more soldiers had died of infected wounds than of the wounds themselves. If penicillin was real, it wasn't a curiosity. It was ammunition. The team grew. Norman Heatley, a quiet, ingenious biochemist, joined as Florey's research associate, a man whose gift was for making impossible apparatus out of whatever happened to be in the building. Edward Abraham worked on the chemistry. Margaret Jennings ran experiments alongside Florey. What they had was a substance that fell apart every time they tried to hold it. Chain and Abraham found that penicillin could be pulled out of the mold broth using ether. Heatley then solved the other half of the problem with an elegant trick. By shifting the acidity, he could pull the penicillin back out of the ether and into water, leaving impurities behind. Freeze-drying turned the result into a brown powder. It was still mostly impurity. The actual penicillin content was tiny, but for the first time, they had something they could measure, store, and inject. By March 1940, they had enough for the experiment Fleming had never run. 8 mice, on a Saturday at 11 o'clock in the morning on Saturday the 25th of May, 1940, Florey took 8 white mice and injected each of them with a dose of virulent streptococcus, certain to kill. Then he injected 4 of them with penicillin and left the other 4 alone. The date matters. That same week, the British Army was being driven onto the beaches at Dunkirk. Britain was days from what looked like the end. In an Oxford laboratory, a small group of people spent the night watching mice. Heatley stayed at the lab through the night, going back after dinner with friends. By 3:30 in the morning, the control mice were dying. By dawn, they were dead. The 4 treated mice were alive, well, grooming themselves. Florey looked at the results and said, reportedly, that it looked like a miracle. He was not a man given to that word. They repeated the experiment on the 1st of July with 50 mice. Every one of the 25 untreated animals was dead within 16 hours. Nearly all of the treated ones were alive 10 days later. But the team already understood the arithmetic that was about to swallow the next 4 years of their lives. A mouse weighs about 30 grams. A man weighs about 70 kilograms, more than 2,000 times as much. To treat one human being, they would need to produce something like 3,000 times what they just used. And the entire supply they had just spent had taken weeks of work to accumulate. They also faced a fear that sounds like fiction, and wasn't. If Germany invaded, and in the summer of 1940, that seemed likely, the mold had to survive. So the members of the team rubbed spores of penicillium into the linings and pockets of their coats. If they had to run, whoever escaped could restart the work anywhere, from the fabric of what they were wearing. The factory in the pathology department. No pharmaceutical company in wartime Britain had the capacity or the interest to make penicillin, so Florey turned his department into a factory. They needed vessels with a large flat surface because the mold grew as a mat on top of the liquid. They tried biscuit tins. They tried milk churns and bathtubs. They tried hospital bedpans, which worked better than anything else and gave the whole enterprise its unlikely permanent image. Heatley then designed a purpose-built ceramic vessel shaped roughly like a stacked bedpan and had it manufactured by a pottery firm a short distance from Oxford. The first batch arrived at the end of 1940. Heatley inoculated them with mold on Christmas Day. Running the operation required labor no one could spare. Florey hired 6 local women. They became known as the Penicillin Girls, who worked around the clock inoculating vessels, harvesting broth, and keeping the culture rooms sterile. Their names are almost never in the story. Without them, there was no drug. The building smelled of mold. The air was full of spores. Every surface had to be scrubbed, and the yield was pitiful. Gallons and gallons of broth to produce a quantity of usable penicillin you could lose on a fingertip. In January 1941, they took the first cautious step toward a human being. A woman named Elva Akers, dying of cancer, agreed to receive an injection, not to be cured, but to find out whether the substance was toxic. She developed a fever, which they traced to an impurity, not the penicillin itself. Otherwise, nothing. It was safe. They now had a drug that cured infections in mice and did no harm to a person. And what they needed was a patient and the courage to use everything they had on one human being, knowing they might run out. Albert Alexander. On the 30th of November 1940, a police station in Southampton was hit during a German air raid. A sergeant was killed. 2 constables were injured. One of them was Albert Alexander, a 43-year-old policeman from Berkshire who had been sent to help keep order during the Blitz. For decades, the story told in textbooks was that Alexander scratched his face on a rose bush while pruning in his garden. It's a lovely image, and it's almost certainly false. His daughter confirmed the truth many years later, and a plaque in his hometown now records it. The wounds on his face came from a bomb. Whether the rose story began as wartime propaganda to hide what German bombs were doing to English policemen, or simply as a mistake that hardened into legend, nobody knows for certain. There really was a rose garden at the police house. That may have been all it took. What happened after was not in dispute. The cuts on his face became infected with both Staphylococcus and Streptococcus. Abscesses spread across his face, into his lungs, into his shoulder, into the socket of his eye. The eye had to be removed. Sulfa drugs did nothing. By February 1941, he was in the Radcliffe Infirmary in Oxford, and his doctor, a young researcher named Charles Fletcher, described him as desperately and pathetically ill. He was going to die, and everyone in the room knew it. On the 12th of February 1941, Fletcher injected Albert Alexander with 200 milligrams of penicillin, then another dose every 3 hours. Within 24 hours, his temperature fell. His appetite came back. The abscesses began to close. Over the following days, a man who had been rotting alive sat up in bed and started to recover. Fletcher watched it happen and understood exactly what he was looking at. And then the penicillin ran out. The drug passed through the body and was excreted almost intact. Florey compared the problem to trying to fill a bathtub with the plug pulled out, so they collected Alexander's urine. It was rushed by bicycle across Oxford to the Dunn School, where Chain extracted the penicillin back out of it and sent it to be injected again. Ethel Florey, Howard's wife and the clinical supervisor of the trials, became known for riding around Oxford on what the team called the Pee Patrol, collecting patients' urine so the drug could be used twice. It wasn't enough. On the 5th day, the supply was gone. There was no more penicillin in England. Albert Alexander improved for a few more days, then relapsed, and on the 15th of March, 1941, he died. His wife and 2 children left the police house. The children went to an orphanage. It would be more than 20 years before the family had any idea what he had been part of. A German journalist knocked on the widow's door in the 1960s asking for a photograph, and that was how they learned. Albert Alexander was not killed by his infection. He was killed by a shortage. Every person in that laboratory understood the difference, and it changed everything about what they did next. Florey made a cold decision. From then on, they would treat children, because children were smaller and needed less. And he decided that the real problem was no longer science, it was manufacturing. And Britain, fighting for its life under nightly bombardment, could not do it. The coat full of spores. On the 27th of June, 1941, Florey and Heatley flew to the United States. Florey carried mold spores in the lining of his coat. America was not yet in the war. What Florey wanted was industrial capacity, and what he found first was a chain of introductions. A mycologist in Washington sent him to the Department of Agriculture, which sent him to an unlikely place, Peoria, Illinois, home of the Northern Regional Research Laboratory, a government facility built to find uses for agricultural surplus. They arrived on the 14th of July, 1941. Work began the next day. What happened in Peoria over the following months did more for penicillin than anything in the previous 13 years. Heatley stayed for 6 months. The lab's fermentation experts asked a question nobody in Oxford had the resources to ask. What does this mold actually want to eat? The answer was sitting in barrels all over the Midwest. Corn steep liquor was a waste product from making cornstarch, thick, sour, and useless. Someone suggested feeding it to the mold. The yield jumped by an order of magnitude. Then they changed the sugar. Then they stopped growing the mold as a mat on the surface and started blowing sterile air through deep vats, so the mold could grow throughout the entire volume of liquid instead of only on top. And then they went looking for a better mold. Soil samples were shipped to Peoria from around the world, from army bases, from expeditions, from anywhere someone could be persuaded to dig up a handful of dirt. The winner came from a fruit market a few miles away. A lab assistant named Mary Hunt brought in a cantaloupe covered in a pretty golden mold. That strain, Penicillium chrysogenum, produced far more penicillin than Fleming's. Bombarded with X-rays at one institution and ultraviolet light at another, mutant descendants of that melon strain produced hundreds of times more. Nearly every unit of penicillin made on Earth since traces back to a moldy melon in Peoria, Illinois. Then America entered the war, and the machine turned on. The War Production Board took control. 21 companies were pulled in. Merck, Squibb, and Pfizer agreed to share research, competitors handing each other their secrets. At Pfizer, an engineer named Jasper Kane argued for adapting deep tank fermentation from the brewing industry. The company bought a disused ice plant on Marcy Avenue in Brooklyn because it had the refrigeration, and rebuilt it into the first large-scale penicillin factory in the world. Crews worked 16-hour days and slept on cots in side rooms. The plant opened on the 1st of March, 1944, with 14 tanks holding 7,500 gallons each. By the end of 1943, penicillin production was the second highest priority of the United States War Department. Only the Manhattan Project ranked above it. The woman who lived while the factories were still being built, the drug was scarcer than gold, and every dose was a moral decision. In March 1942, a 33-year-old woman named Ann Miller lay delirious in New Haven Hospital in Connecticut. She had miscarried a month earlier and developed a streptococcal infection of the blood. For 4 weeks, her temperature had spiked past 106 degrees. Sulfa drugs failed. Transfusions failed. Surgery failed. Her doctors had run out of ideas. By coincidence, another patient on the same ward was a Yale physiology professor who happened to know Norman Heatley personally. Phone calls were made. Approval was granted. And 5 grams of penicillin, half of the entire supply then existing in the United States of America, was flown across the country and driven to the hospital by a state trooper on the 14th of March, 1942. Sit with that number. Half of America's penicillin was about a tablespoon, and it was spent on one woman. Her urine was collected, the drug extracted and re-injected, because there was nothing to waste. By the next morning, her fever was gone. She ate breakfast. She recovered completely, and she lived another 57 years. At the end of 1942, the United States had enough penicillin to treat fewer than 100 people. In June 1943, American production was 400 million units. By January 1944, it was 20.5 billion. By June 1944, it was around 100 billion units a month. The beaches. On the 6th of June 1944, Allied soldiers went ashore in Normandy, and in the packs and medical kits that landed with them were roughly 3 million doses of penicillin, most of it produced in a converted ice plant in Brooklyn. Understand what that meant on the ground. A man hit by shell fragments in a French field had soil, cloth, and bacteria driven deep into his body. In the war his father had fought, that man's realistic future was gas gangrene, amputation, or sepsis, and the surgeons had known it and had cut fast and cut wide. Now a medic could give him an injection, and the infection that would have killed him simply didn't start. The numbers tell the story more flatly than any description. In the First World War, roughly 18% of American soldiers who developed bacterial pneumonia died of it. In the second, with penicillin, that figure fell to under 1%. Photographs from field hospitals in that period show something new. A small table with rows of glass vials and a syringe, and a queue of men waiting. Not for surgery, for a shot. And then the war ended, and the same thing arrived in ordinary life. Penicillin went on sale to British civilians by prescription in June 1946. The price collapsed. A drug that had been worth more than its weight in almost anything became something a pharmacist handed over for pocket change. Ward by ward, the septic wards emptied. Puerperal fever, which had haunted childbirth for the whole of recorded history, became a treatable complication. Scarlet fever stopped being a word that frightened parents. Rheumatic fever, which had been permanently deforming the hearts of children, could be headed off with a course of pills. Within a single generation, the red line climbing an arm stopped being a death sentence and became an inconvenience. The prize, the patent, and the warning. In 1945, the Nobel Prize in Physiology or Medicine went to Alexander Fleming, Howard Florey, and Ernst Chain. Norman Heatley, the man whose back extraction method made purification possible, who designed the vessels, who traveled to Peoria and stayed for 6 months, who ran the assay method that the entire American industry adopted, received nothing. It took Oxford until 1990 to correct the record in its own way by giving him the first honorary doctorate of medicine in its 800-year history. There was another absence. The Oxford team never patented penicillin. Chain argued that they should. He was overruled on the grounds that patenting a medicine was unethical. American companies patented the production processes instead. Britain, which had discovered and developed the drug, ended up paying royalties to import it. The public settled on a simpler story. Fleming, modest, quotable, photogenic in his cluttered lab, became the man who discovered penicillin, and the mold that blew through an open window became one of the most famous accidents in history. Florey, who disliked publicity as a matter of principle, largely disappeared from the popular version. Heatley disappeared entirely. As one Oxford scientist later put it, without Fleming there would have been no chain, without chain no Florey, without Florey no Heatley, and without Heatley no penicillin. It took all of them, and it took a war, and it took a melon. And in his Nobel lecture, in December 1945, at the exact moment of triumph, Fleming said something that almost nobody wanted to hear. He warned that penicillin would one day be sold to anyone, that people would take too little of it, and that by exposing bacteria to doses that didn't kill them, they would make those bacteria resistant. He was describing, precisely, the problem we now spend billions of dollars trying to solve. He said it in the same speech in which he accepted the prize. What the blister means. Now somewhere today, a child falls off a bicycle and scrapes a knee raw with gravel. A parent cleans it, puts a bandage on it, and thinks about it for perhaps 90 seconds. A week later, a small pink line is all that's left. That 90 seconds of not worrying is the whole story. It's the thing that was bought. Not with a flash of genius on a September morning. That was only the beginning, and it went nowhere for 11 years. It was bought by a bad-tempered Australian who understood that the hard part came after the discovery. By a refugee chemist whose family died in the camps while he worked. By a quiet man who built the equipment out of bedpans and pottery. By 6 women in Oxford who spent the war harvesting mold around the clock. By a lab assistant in Illinois who brought in a melon. By engineers who slept in a Brooklyn ice plant. And by a policeman named Albert Alexander who got better for 5 days and then died because there wasn't enough. We inherited the result and forgot the price. That's what safety does. It erases its own history. The reason the death of a 16-year-old boy from a blister on his toe sounds absurd to us is that a specific number of specific people did a specific amount of work, most of it tedious, much of it unrewarded, during the worst years of the 20th century. And Fleming's warning is still standing there at the end of the story, unanswered. The world he described, where the drugs stop working, where the small wound becomes dangerous again, isn't a hypothetical. It's the world we came from. It took 11 years, a world war, and the entire industrial capacity of 2 nations to leave it. Nothing guarantees we get to stay. So here's the question I'd like you to answer. Which part of this story changed the way you see it? The 11 years the discovery sat unused, or the man who was cured for 5 days and then ran out? Tell me in the comments. If this made you look at something ordinary in your medicine cabinet a little differently, hit like and subscribe, because the things we take for granted almost never happen by accident.